Welcome to a lesson with Dr. Powell. Let's practice showing which limit properties we're using with an infinite limit, or a limit that is as x goes to infinity. So let's take the limit as x approaches infinity of something like 5x to the fourth minus 3x plus 2 all over 2 minus x to the fourth. The limit as x approaches infinity. Now, if we try to kind of loosely think of what this looks like and behavior-wise as x goes to infinity, this looks pretty infinite. And this likewise goes to negative infinity. Now, infinity over infinity, as a rule, is not really well defined. For instance, what if you had like 5x over x? What does this go to? And well, you could, in your mind, you could think infinity over infinity. So that's must be 1, right? No, that intuition is wrong. Please do not ever think that. This is actually 5, right? And as it goes off to infinity, it stays at 5. There are lots of ways of getting infinity over infinity. And infinity over infinity is a representation which really is not well defined. We don't know what it's going to be equal to. It could be equal to any myriad of things as an expression, so it's just not defined. We cannot say infinity divided by infinity. So we can't treat infinity like a number in that way. It's just an idea. It's an idea of going on forever. So keeping that in mind, we can't just simply plug in infinity here when we're taking a limit. Instead, we're going to use limit properties. And let's practice actually showing those limit properties and how they work. So, first of all, we can multiply, well, this is a fraction, so you can multiply it by 1. Multiplying by 1 is the same thing as multiplying by the limit of something as x approaches infinity, which is 1. Well, why not like something like this? 1 over x to the fourth divided by 1 over x to the fourth. Which, you know, in some sense, you could think, well, that looks like well, as x goes to infinity, and this gets real big, 1 over real big is like 0. This looks like a 0 over 0, which is not well defined either, just like infinity over infinity is not well defined. However, we know what this is because along the way, we can see what it is. For any value of x that's just on its way there, this is the same as this, so you get cancellation. Here, like if you plugged in 500, for instance, you'd definitely get cancellation. And so that would be 1. Meaning that the whole time you're 1 as you keep going. So the limit is 1 eventually. So this right here has a limit of 1. So you could think of this as just being 1. Now, do you remember a property of limits? Limits pass in and out of continuous operations, including multiplication is a continuous type operation. So it can pass out of it from the 2 different parts of the multiplication to the outside. That's the first property of limits that we can use. Now, why did we choose to multiply by 1 over x to the fourth divided by 1 over x to the fourth? We'll see that as we go. All right, so we're left with this times 1 over x to the fourth all over 2 minus x to the fourth, 1 over x to the fourth. Notice when this multiplies in and distributes, we end up getting something like this. 5 minus 3 over x cubed plus 2 over x to the fourth. In the denominator, we end up getting 2 over x to the fourth minus 1. Now you might see why this was nice at this point, perhaps, but maybe not, so let's specify. Well, now, since this limit and so is going across these operations which are continuous, division, subtraction, addition, and so forth, it actually can plop into and throughout this whole thing. It can be applied to every single term here. So this limit can pop to here, to here, to here. That's another limit property. And we'll write that out. But when it does, notice that this part will go to 0. That part will go to 0. That part will go to 0. And we'll just be left with 5 over -1 for a final limit of -5. Notice what we did. We wanted to look at the leading terms. And so we divided by something, so this was out in the open, so we wouldn't have infinity over infinity anymore. In other words, we're multiplying by something so that plugging in will make sense, just as we had before, same type of idea, but by plugging in something, or by multiplying by something on top and bottom, so that plugging in will make sense. And that's kind of how we did it. I mean, it'll be different each time. Takes a little bit of strategy, but here, if you have a leading term, it'd be nice if that leading term were a constant. So hence multiply by 1 over x⁴. Okay, so maybe to finish this off, how would we actually write this out? So what I would do is, and maybe I'll see here, write it up here. And actually write the limit as x approaches infinity of, well, that limit would pop in, right? Okay, so that limit would pop in the fraction now, because it's popping in across all the operations. Limit as x approaches infinity of 5 minus the limit as x approaches infinity of 3 over x³ plus the limit as x approaches infinity of 2 over x⁴. If we really wanted to be facetious, I suppose we'd put the limit on the inside of this and that, but let's not go that far. I mean, technically speaking, that's what would be happening, but let's just kind of at least write out some of the steps. Minus the limit as x approaches infinity of 1. See, it passes through that multiplication by negative and here and there. So looking at this, then we can plainly see that this limit right here, 2 over something really big, it's just 0. 3 over something really big, that's just 0. 2 over something really big, that's just 0. So we end up just getting, and this limit's 5, that limit's 1. So we end up just getting 5 minus 0 plus 0 all over 0 minus 1. So we end up getting -5 for our limit. Thanks for watching.